Let's talk about electromagnetic induction. Okay, this explains how the electric motors work and how the generators work at the same time, which I will explain how the generators work, and let's see if we get to electric motors. It's a similar idea. Do you ever feel like universe knows what your intentions are and gives you exactly opposite? Known as Murphy's Law or some of these things, right? Universe hates you, right? You get the feeling. It is true. It's actually physical phenomenon, observable physical phenomena. Really? Say there's a loop or many loops, so coil, solenoid, right? So you can feel the force. And you connect that thing to some kind of resistance, light bulb, or in this case, amp meter to measure the current. And you shove the North Pole of the magnet in to this loop or coil, and then it'll fight you. This thing becomes an electromagnet by itself, and it resists you. Seriously. But if the magnet is stationary near the loop or coil, then there's nothing. It doesn't do anything. Now, if the magnet is already inside or nearby, and you try to pull it away, then this thing becomes a magnet in opposite direction to pull it back. So this will always do exactly opposite of what you want to do. It's amazing, isn't it? It's nothing. There's no power source anywhere. It's just a stupid coil connected in a closed circuit. And this knows what you want to do, and it'll do exactly opposite. Okay, Michael Faraday, one of the most famous physicists and also chemist, well, yeah, and mathematician, observed this and then tried to come up with the explanation. And so what we are doing is this magnetic field will induce the current in a loop. But if you just the presence of the magnetic field does not do anything like this case, it's the change of the magnetic field, only the motion. So, and I'm going to explain the whole theory behind it later, but let's just learn how to decide. Here's a loop. Say here's a loop like this. And then we are trying to bring the magnet. I'm going to throw it a little bit farther away. So this is the north and this is the south, right? So if I shove the magnet in this way, then it's as if this thing is creating a magnet of its own to fight you. You know what I'm saying? Which means the direction of this current has to be, remember, it has to be this way, right? Right-hand rule. You wrap your fingers around. Okay, now we'll look at this case. So here's a loop again, and here's a magnet that you control. And this is, oh, let's just keep north here to be consistent with and south. And then now you want to pull it away, right? And then this is what happens. There will be a current, but now this thing becomes south and this thing becomes north to fight against this motion. It attracts you. So the direction of the current in this case has to be that way, right? Because north pole, your thumb goes again, right? Along this direction. So this is essentially what Faraday's law of induction is. Okay, we're gonna get to why this happens, but it's amazing, huh? Okay, here's the motivation, okay? Why things happen the way it does. Let's say there's a conductor, metal bar, with free electrons, right? Electrons can move around. And magnetic field, inside the constant magnetic field, and that field is going into the page. Remember this symbol, X means going into the page? Okay, and then we are going to slide this metal bar to the right. Momentarily, then what happens to these electrons? Okay, So let's try to remember this force, right? Force of the magnetic field was Q, the amount of charge, times V cross B. Do you remember that from last time? Okay, so right hand rule again. So if we stretch our fingers into the page and our thumb this way, so this is your hand, fingers into the page, and then your palm is that way, right? So force will be upward. That makes sense to you? However, that is if this is positive charge, then the force will be upward, remember? But this charge of the electron is negative, so it actually moves. Or if you have to do left-handed rule for negative charges. You know what I'm saying? Or figure out the right-handed one and then do the opposite. So electron will move downward this way. Good? That makes sense to you? So far, so good?
I just want to make sure in which direction is the whole piece of metal moving?
Oh, this direction, to the right. Right? That's why your thumb, imagine this is your hand, your thumb sticking out and fingers are into the page. Okay? That means there will be more negative charges here and there will be more positive charges here, right? That implies there's an electric field moving upward, correct? Right? Because how else the charges would move without, because that, when we say electric field, I mean, it's like fictitious field lines that moves the charge, right? And there will be a potential difference between this part and this part. Okay, so let's try to calculate how much that is. Okay, now this is perpendicular, right? The velocity and the field lines are perpendicular, so cross product gives you 1 sine theta, sine 90 gives you 1. So the magnitude of this is QVB. Good. However, the force of the electric field, because it will create the field to move the electrons, and that happens to be Q. Many of the reviews are built into these, right? When you say potential, I mean, the force means, your unit charge times the field. Good. So we equate the two magnitude-wise. So we have QE is equal to QVB. And Q's cancel out. So our amount of electric field is equal to B. Good. And then how do we calculate the potential difference? We integrate opposite integral moving, right? But in this case, it's just constant amount of electric field with that distance. So it's just same as multiplying it by L. Right. Do you remember that? Here, delta V was equal to ED, distance or delta X or whatever distance. Okay. So now it gives us a motivation why there will be a current, right? Because it's a moving charge after all inside the magnetic field. And the key is this is a conductor, so it has got free electrons, right? Instead of thinking with the electrons, we'll just think of a positive charge, although it's not, but according to the convention, okay? Now, but it has to, because eventually this will not go anywhere, so there won't be an actual current unless this is closed circuit, so that there will be a flow, right? So we have to have a loop like this, and then there has to be a resistor, okay? And then it'll create the current, exact same situation. So if that looks like, it'll create the current moving upward, correct? So far, so good. Okay, and then it'll go through the resistor, and then it'll go around the circuit like that. But what happens if this side is also inside the magnetic field? Let's say magnetic field extends out here as well, like that. Then do you see that there will be free electrons here with the same amount of movement? So this will induce the current going upward as well. And these two fight each other and cancel. So we get nothing. Right? So the whole key here is this thing, this end, one part of the circuit has to be outside of the magnetic field. That makes sense to you? And situation in this is exactly same as if there's a battery. What was this symbol? E again? E? It means EMF, right? Electromotive force, but it's really not a force, it's really delta V. But for some weird reason and convention, they just call it EMF a lot. So it's like, the same thing as potential difference. People call it voltage all the time, okay? So this end has to be outside, and this end is the one that is moving. So usually this is some kind of metal bar sliding on this track, also conductor, okay? So far, so good? Okay, now let's count. Let's think like this. Let's count the flux count inside this thingy. Flux, remember, is like when you say magnetic field or electric field, that is more like a field density. So more area that you have, by moving it to the right, you're exposing, and you're introducing more flux lines in here. So it's proportional to the area of this thingy, right? Okay, so flux count here is, it's a similar thing as Gauss's law. This is a little bit misleading. Remember this? This was E dot dA in Gauss's law. Okay, so that's the total flux count. It is really misleading because he said this circle means enclosed surface, but in multivariable calculus, so if you're in it, it's really not. It's just a loop, so it's like it gets confusing. But your book does that. What it is really is the double integral over this area, okay, area, and then B dot dA. This is more correct mathematical notation. Okay. Now, once again, then we have a dot product. Okay, dot product. Let's look at this picture. So if this is a tiny bit of a dA, and if we are at an angle, then this does not count the regular flux, only whatever is perpendicular to this, right? So if I draw it, only surface that is perpendicular to this. Did I do? No, 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 no. I messed this up. I have to draw it like this, right? Only this thing perpendicular to these field lines are the true flux count. And this is the angle between, right? So this is B times the area times cosine theta is what that dot product is. Similar to Gauss's law, okay? Now, in our case, it's perpendicular in this picture up there, this one. So B is constant. So we can take it outside. And then we have this double integral A, the region A, and then the A. Good. And then that whole thing is the area of this rectangle, isn't it? So you'll see that a lot. And then that makes sense. Total flux count is its density, which is what we call B field, magnetic field times the area. That gives you the total amount. And in our case, now, here, let's call this side L and this side X. Because X increases, so it's a variable X, so this bar slides to the right, and this L is the width of these tracks. Yes?
So here, would there be some sort of sine theta happening in that equation you've done there?
Oh, cosine theta. But see here, let me put it here. Cosine theta happens to be cosine 90.
Right, so when they're straight on, it doesn't.
Right, cosine theta. Yeah, cosine 90, which is 1. Okay. Now, so that A is B times L times X, isn't it? Okay, here's a motivation. It's not exactly a derivation, but here's a strong motivation of how to calculate EMF or the potential difference created by changing the magnetic field. Because we're changing the not the magnetic field, but total flux count within our loop, our circuit. Okay? So let's take a derivative of this flux now, total flux with respect to time. So that is now, that's the derivative of BLX. You see BL is constant in our setup. So that is BL dx over dt. Isn't this velocity? So what we have is BLV. Good? Say yes. Why does that look so familiar? BLV, where have we seen that? Here, huh? BLV. Ah, so that is the potential difference, right? Opposite. So this is indeed negative of delta V from here to here, here to here. You get it? And that's what they call EMF, induced by the changing the magnetic field or flux count. Okay? So this is Faraday's law. Good? So they define this induced EMF or potential difference will be negative of derivative of the flux count inside that loop, whatever. We have to have a circuit in this business, so whatever your circuit encloses. Good? Now we'll take this example. So we have a loop of wire enclosing an area, okay? Now that area will stay the same, but now our magnetic field or field density varies in time, given by this equation. Okay, so this is our change of the field. Whenever there is a change of the flux count within our closed circuit, it will induce a current. So what would be that current as a function of time? Okay, and then here, magnetic field diminishes in the exponentially decaying manner. Okay, so then this is equal to negative of derivative of the flux count. Good? Okay. Now, once again, this is a integral, but constant area, so we can just say that's negative of the derivative of your area A times B function. Good? Okay. Now that is equal to negative derivative of A, and the B, of course, is B maximum original times e to the negative at. And at, this is A. An exponential function is easy to take a derivative. Chain rule cancels that sign, so we'll have lowercase a, chain rule, a, b, max, and then e to the negative at. So amount of EMF will be also exponentially decaying, because after all, the EMF, the potential difference induced by the change is change of the magnetic field. It only depends on the change So if that magnetic field does not change as much, more mathy way of saying that is only depends on the slope of this function. You get it? But we get a positive here, okay? If this is a negative slope, but that there's a negative sign. You get it? Okay, all good? Okay, now we'll actually integrate and compute the same thing because we conceptually talked about it. So now we shall integrate. So it's exactly the same setup as before. We have a sliding bar with a velocity. Initial velocity is given. Okay, and then this will create a current. Remember, flowing that direction, right? Exact same setup as before. Okay, and then now we have to figure out, wait, let me ask you guys a question. Will this slow down, move at a constant speed, or speed up?
Do you mean like, oh, if it's being affected
Yeah,
by
if you, let's say that this is frictionless contact, and then we push this bar so it'll slide, right? Which will induce the current going around this way. Will this bar, without the friction due to the track, move at a constant speed forever? Will it slow down or will it speed up?
um, would it slow down because that means that it would be spending less energy on like generating electricity?
Yeah, it has, see, conservation of energy, if it's not going to be in constant motion, well, let's just take out the obvious case. It will not speed up because if it speeds up without any energy source, we have just created a railgun. And then this will increase the speed forever and ever, and then that's next infinite amount of energy, which cannot happen. So there's no way it will speed up. Constant motion. See, having a current, meaning if this is a light bulb, there will be a light, which means that energy has to come from somewhere, right? Where does it come from? This kinetic energy of this thing will be converted into electric energy. So it has to slow down because we are draining energy from it. So like we don't lose anything, but we don't gain anything at the same time. Okay? Alrighty, so this thing has a mass m and all that usual setup. So we'll compute what would be the velocity as a function of time. It'll slow down by how much? What kind of linear function or, right? Okay, so common sense. What does common sense tells you? If you imagine there should be some kind of force, dragging force, the other direction, so that's why this will slow down, right?
Well,
Once again, universe gives you opposite of what you want. So if you want to throw this that way, something will drag you behind.
um, in this case, in the picture,
Yeah.
maybe something is different with the picture, but wouldn't the back part actually not have any field around it?
Which part? This part?
Yeah, because it has a field around it, wouldn't that be meaning that there's no like flow of electricity?
Oh no, no. Oh, okay, because of the other case that I explained here, right? No, in that case, I was moving. These two are moving at the same, right? This is moving and this is moving. But this thing is remaining same, so this part, electrons here does not feel any forces, right? So there's no potential here. This is the only thing that's doing the moving. You know what I'm saying? So this derivative, the way we defined here, it has to do with the change of the flux count inside our circuit. That's the only thing that matters. So by increasing this area, I'm increasing the amount of magnetic field flux lines. So that will still induce a current. How about that? Maybe I should have made that a little clearer earlier. Okay, so let's just think conceptually. If it goes down linearly like this, then it's going to come to an abrupt stop, right? It's like that can't be the case, right? So you would think this will be more, this is the original, and then gradual, you know, exponential looking That kind of slow down. Let's see if we really get this. And then, do you remember from mechanics that terminal velocity problem? If there's a drag, and then that will reach the terminal speed. It's that kind of idea. But in this case, if you roll something on a surface, then because of the friction, it slows down and it comes to a stop like that in that manner. So we expect velocity to be gradually winding down to zero. Okay, let's see if we really get that. Okay, so we start with calculating EMF voltage, which is, and instead of memorizing any of these results, I advise you to just do this each time. It's not that difficult calculus, although textbooks don't. And once again, let's just figure out the total flux count. Instead of integrating, that is just the density of the field times the area, which was L times X, wasn't it? I mean, we just did this a few minutes ago.
Well, would it be 10
Huh?
Right.
Now we are going to take a derivative, so this becomes V. So that is opposite of BLV, which is what we had a few minutes ago. Literally, I'm redoing the whole thing. Which means now electric current, this negative sign is a little misleading because that's not the reality. We have to just upward, downward, and then direction of the field, it just does not line up. So we have to use a right-hand rule to figure out the direction of the current, which is upward. So then the current is the absolute value of the potential difference divided by the resistance of this thingy. Hopefully you've been reviewing these, right, circuits with the resistor. Let me write it here. Delta V is equal to IR. Remember that? Yeah, so we divide by R, then we get the current. And substitute this thing in, so we have BLV over R. Okay, so far so good. Now, if there is a charge moving, here's the thing. Charge is moving inside a magnetic field. That experiences a force now, right? So let's do the right-hand rule again. You put your thumb along, that doesn't look like thumb. Your thumb along this, and this is your hand, and your fingers are still into the page. And then force is to the left, isn't it? So due to this current, amount of force that is exerted on this bar is to the left. So it creates a drag, which will reduce this velocity, as we expected, right? Because we have to drain this energy from somewhere, and that we are converting the kinetic energy of this bar. So the force due to magnetic field is equal to IL B. Hopefully you remember this. In case it's a point charge moving, then it was Q force was Q cross V, Q times V cross B. And in case it was a current, continuous stream of current, we took a derivative, and this was I times B sine theta. That idea? Right. That makes sense to you? Yeah, this negative sign, maybe I shouldn't put it right now because direction just is difficult. It's just to the left. Let me just write left. Right? It was like that negative sign, I was meaning opposite sign that this. Maybe I should put negative sign back. What do you say? All I mean is the opposite direction of this velocity, the positive x direction. So yeah, let's put the negative sign back, right? Because this is positive x direction. So
In
to the
that
left.
case, maybe you would put the left in parentheses just to make sure that it doesn't
Yeah, okay, left in the parentheses, right? That's all this means. I just decided the direction are through cross product. Okay, so far so good. Okay, now then we have I, right? This is our I, so we substitute it right there. Okay, so what we have is negative b squared L squared over R constant, R meaning the resistance, not the radius of anything, times V. Okay, V is our variable V, which will decrease as a function of time. At the same time, of course, F is equal to MA, which is, of course, M times dV over dt. We equate the two, then we get our differential equation. How about that, huh? Then it's all downhill. It's only a differential equation. So if we equate it to MA, this is A, is equal to negative B, oh, that's fancy B, B squared L squared over R times B. With me? So dV over dt is equal to negative B squared L squared over MR times B. And then we have done this before, right? We integrate both sides. We separate, so dV, well, integral, well, whatever, negative. Let's read it. This is a lot to write, right? So convention-wise, we can just call it K or something, right? But don't write K yet, because I'm going to write whatever the book does, which is 1 over tau, which is kind of convention. So instead of constant, 1 over constant, this whole thing, reciprocal of this whole thing. You get it? And then we have the v dt. Now v is gone, so dt. Good. Then we integrate both sides. Okay, say I'm going to say tau here is reciprocal of this. So mr over p squared r squared. Good. Okay. So integrating this, I forgot. I have to divide both sides by this v, right? Let's just put it right there. Right, that v, I forgot. Okay, so this is ln, and we are sure antiderivative of 1 over v. And then right hand side, we pick up t here, so negative t over tau. Tau is some kind of half-life looking thingy. Okay, and plus c. With me so far? So solving for this v, absolute value of v known also plus or minus then e to d negative t over tau plus ca. But we rewrite this all the time. So this a, wait, we haven't used a here, have we? No, we have not. So a, it is e to the negative t over tau. And my a, of course, here is plus or minus e to the c. We relabel the constant. Good. Now we can say initial condition at velocity at 0, which is what they call vi here in this problem. So the left-hand side becomes vi, and you substitute 0 here, so it just becomes a. So finally, as we expected, velocity as a function, substitute this back in, is v initial, and then e to the negative t over tau. And once again, tau is equal to an r over b squared L squared. And whatever we predicted here is true. Good? Question? Okay. Instead of the bar sliding just sideways, now what happens if we rotate it? You know what I'm saying? So there must be some kind of, pivot point, and this whole thing rotates. Okay, well then. We cannot just say E, so like dE, tiny little e, and then we will integrate, of course, right? Remember, E was BL, let me start here. E, electromotive force, was BLV. You know what I'm saying? So that means dE is equal to, this is the thingy, that tiny infinitesimal, right? The whole thing is L, and that thingy is what we call dr. So BV dr. That makes sense to you? Am I missing a negative sign? I think I am missing a negative sign. Let's see. E is equal to BLV. All the way up here. Well, it depends on which side is up, which side is down. We'll just keep it right. That side is positive, this side is negative. Okay, well, let's say this is a magnitude. Good. Okay, now we are going to integrate this. Okay, but remember this v is a function, right? And then we're integrating that function in terms of r. So I need to know what that v is. What is v?
This would be like
There, right? R omega, because they tell you, right, rotational speed, angular velocity, and then r is whatever r is from here to all the way there. You know what I'm saying? Okay, so that's our variable r. Good. Okay. Oh, I screwed up. Looks like pivot point is right here. Right? So R is only this much, is R. So R varies from 0 to L. How's that? Okay, well done. Now we can integrate. So E is equal to from 0 to L of B, and our V is, of course, R omega. Let's write omega first, then R dr, because this R is a variable. Good. And that is equal to B omega R squared over 2, varying from 0 to L. Substituting, so we have 1/2 P omega L squared. It's the magnitude of EMF due to rotation. And whether you decide to throw negative sign or not depends on which direction is a higher potential. How's that? Good? Okay. There's a thing called Lenz's law. Lenz's law. Lenz's law? Lenz, I think it's Lenz, German. Okay. And this thing basically says universe gives you exactly opposite of what you want. Okay. Remember this setup, right? Still our same idea. If we slide the bar to the right, then it creates the current upwards, right? And then if there's a loop of current, then there will be a magnetic field created by this thingy, right? What is the direction of this? Right hand rule. Put your fingers around this and direction of your thumb. So it comes out of the page. Do you see that? Your fingers around this way. Here's your hand, and then direction thumb is pointing outwards. You know what I'm saying? Which will eventually cancel this magnetic field. I told you that universe always gives you exactly opposite, right? So what happens is, in many cases in electric motors, this always happens. Electric motor is using magnetic field and electric current to create the force. But when you create the force, it creates this the magnetic field that's in opposite direction and cancels the original one. So your electric motor can reach only a certain speed, and after that, it just puts the natural brake on it. It's known as a back EMF, and that will always happen in the opposite direction. Let's think about this case. So if you pull the bar to the left, and then the flow will be opposite. The current will be downward, right? So if you put your fingers around, wrapping around this way, then direction of the electric field, right? Fingers around, wait. Yeah, direction of the, oh yeah. I said something that's a little misleading. Okay, let's go back to the first case. Amount of the flux count in this page is increasing in this first case when you move the bar to the right, correct? Then it still creates this field out of the page to cancel whatever you're adding. You get it? However, in this case, the direction is reversed, so amount of the count, because this bar is closing, so this area is decreasing. So that amount of flux count is decreasing. You're losing the flux count by closing this thing down. So it creates the additional magnetic field in the same direction into the page in order to keep this flux count constant. Right? That's what Lenz's law is. It will try to resist you by doing opposite of what you are doing. So the whole thing inside, they like it to be constant. They meaning universe, force, whatever you call it. Okay. Remember this case when we started this class with? So idea is the same, but I drew this picture, but let's just think about in light of what we just learned. When you shove the North Pole into this loop, right? What you're doing is the field density. Remember when this thing was outside, inside, so then more of these field lines will be inside the loop now by shoving this magnet closer in, because these things expand out like that. So you are increasing the flux lines here, right? That will create the electric current that way, and this side becomes North Pole and this side becomes South Pole. And then there will be many of these type of questions on the multiple choices on your AP. So the way you think is universe always gives you opposite. You get it? So you decided this side is north to fight this motion, therefore current has to be that way. Yes?
It's kind of like air pressure in the cylinder. So if you push it in,
Yeah.
it will increase.
Yes.
If you pull it out,
Yeah, in a syringe. Yeah, it's exactly like that. And then if you pull the North Pole out of it, you're decreasing the amount of flux lines inside, so that the induced current has to be in this direction to create the South Pole here to fight you. This is Lenz's law. Okay, any questions? So that was more conceptual question, which happens and which shows up a lot. Okay, now let's talk about this. So we have a loop, conducting loop, length L, width W. And you're going to move that across the magnetic field going into the page. Okay, and that will induce EMF. Okay. And then now they want you to plot this as a function of x. X meaning distance from here to where the location of this thing. Okay, so we have to plot the flux count as a function of x, and b, we have to plot the EMF as a function of x, and then lastly we have to plot the force. Okay, dang, huh? Well, that's a handful. Okay, and let's say 0 is at the edge of this field, so when this loop is about to enter is 0, right? So this edge is the location. What we mean by that is when we say x, that is x, that distance. You know what I'm saying? Okay. So do you see that amount of flux count inside this loop is changing? Do you see that? As this thing enters it, there will be more magnetic field inside this loop. Okay, so let's think. It has to go up in some kind of linear function, correct? Yes.
So here it's just, is it just passing through the field at a constant velocity?
Yeah. Oh, yes, constant velocity, v. So it has to be a linear function because it's constant speed, and the amount of this area increase is exactly same. So it has to be constant slope, constant derivative. Good. And as soon as this back end enters the field, then this flux counts remains constant as it moves through, right? So it has to be some kind of constant function like that. Good. Now, when it exits this thing, then you are losing the amount of flux count. So that has to be very symmetric and coming out like that. And once the whole loop exits, then this will just go out. So this has to be our function. Okay. Well, how much? Like, how high is this? Can we tell what this x value is right there? That is the entire loop entering. So this needs to be WA. And then when it starts exiting, then this part has to be 3WA. Well, how do I know that? Because it's given to you here. 3W is the total width. This is 3W here, given by the problem. Okay, so it's got to be 3W, and when the whole thing exits, that's another W, so this has to be 4W. You agree that much? Okay. Then we have to figure out how high this was, right? Okay. Instead of memorizing, we have done this before, but let's do this one more time so that you get the hang of it. Total flux count is the integral, like that. But then this is constant magnetic field, so we can bring it outside the integral, and then dA. Good. And that's the total area. But then area in this case is L times X. Correct? So this maximum has to be BLX. Good? However, what's the X value at this point? W. So this has to be BLW. That makes sense to you? Okay, now, after that, this is easy. EMF is negative derivative of that flux count. Good? Shall we just conceptually think or do the calculus first? Your choice. We can do the calculus, then draw it, or draw it, then do the calculus to figure it out. Let's draw it. So it's the opposite of the slope of this thing, right? What's the derivative of linear function? It's constant, negative constant. So it has to be something like this, eh?
Yeah.
Right? And this is W. And then we still don't know what that slope is. Well, we can calculate it from there, right? Or we can differentiate it. You want to differentiate now?
Well, we could just take the measurement of B all W over W.
Uh-huh.
B1.
So this is the, okay, let's take a derivative. Okay, this is healthy. BLX, correct? And these two, BL is constant. So we have dx over dt, right? And that is, remember that's B. So this is negative BLV. And here's a constant function, derivative of constant function. That slope is 0, so this part will go out like that. And this is the 3W now. Good. I'm going to write it at the bottom. And after that, it has to be symmetrical, like that. And that side is positive BLV. Good. And then it continues out like that. That makes sense? Okay. Now, what about the force? Not force given to by the field, but you have to do some work to drag this thing at a constant speed because remember, this nature will fight you, right? So that's the force that you have to exert to overcome whatever the force that this thing will pull back. Okay? Okay, so in order to do that, here, F is equal to magnetic field L times I, remember? Or IL? I keep mixing this order up. The force of the due to magnetic field on a current, well, this current carrying wire or conductor. And of course, I is absolute value of EMF, your potential difference divided by R. And we have this here, so this is BLV, absolute value, over R. Good. And we plug that I in here. So what we have is B squared L squared velocity over R. Look familiar? Because we had that earlier. Okay, now, so here it has to be constant amount of force to drag it. Okay, because you're changing the amount of flux count. But once the entire loop enters the field, then it's zero. All of a sudden, it doesn't require any more force. It just moves easily. And then once you're exiting it, it'll require same amount of force again. And then once the whole thing exits, it just goes easily. Nature just does not want you to change the amount of magnetic field flux count inside the loop, inside the conducting loop. As long as it remains constant, it doesn't care. So always remember that nature does not like the change of magnetic field flux count. And it'll fight you. You have to do some work to do it. Okay, well then, more exciting case. Say there is a conducting metal circular inside the magnetic field. And if, as long as this field is constant, nothing happens. Okay? But let's say this thing is a function of time. Then how are they related? Okay. And then this diagram already has electric field that way, so we'll calculate it that way. Suppose due to the change of the magnetic field, current is moving in that direction, right? So electric field is thrown like that. So we'll have counterclockwise current. We have to calculate the potential difference. Do you recall that it was like this? Over some curve C, our line integral from multivariable calculus. Okay, but this is a potential energy that you're trying to gain, right? So if you move in opposite direction, that negative sign is there so that this is not work done by the field, but this is you doing the work against. So opposite direction, that's moving this way, that line integral, right? So if I change the direction, it'll just be, so say the potential difference from point A to point B, and let's say point A is here and point B is there, okay? That's got to be just the integral of E dot ds, dr, whatever. Good? Right, now here's the thing. What happens then if I try to calculate the potential difference all the way around? From A, B, C, D, back to A. If the field is conservative. And in this case, it's not. It's just this, right? And usually, see, most of the physical field is conservative, right? This is the one that's not, because there will be a permanent current go looping around forever. So it cannot be a same potential. You know what I'm saying? So it's like potential difference is a little weird because potential difference has to have a starting point and ending point. So this is a higher potential and that's a lower potential, and you integrate that much. But right, this thing is perpetual loop. Now, magnetic field, presence of the magnetic field is not going to create a current like that. That's just free energy. If the field changes, if the field strength changes, then there will be some kind of loop. And we are trying to figure out the direction and all. Okay? So at least we understand this is non-zero, non-conservative field, so non-zero integral. Okay? Now, but at least electric field is constant, eh? So we take it outside of the integral and we just have this. Well, is it constant? Well, it depends on how much this thing changes, but yeah, because it's changing uniformly. It's not like this part, it's not a function of space. It's not this part changes more than that part, right? The whole thing changes, so amount of field electric field that it induces is constant. Well, that is then E times 2 pi r, the circumference of this thingy. Okay, I'm gonna let that sit there now. Okay, change the color. Let's compute EMF. EMF, of course, is opposite of the derivative of flux count, eh? And that is opposite derivative of B times the total area. We don't have to integrate it. That gives you pi r squared. Is the total area inside the loop. Okay, the BA. I mean, we have seen that BA all the time. This is BA. You get it? Okay, so this is same as, now we take a derivative of this, and then pi r squared is constant. So we have negative pi r squared dB dt. Remember, b is a function of time, so it's dB dt, whatever that function is. Okay? Now, we equate the two. EMF is like driving potential, but then you cannot say potential difference because it's a closed loop, right? But that's the amount of voltage that will move the charges around. So we equate the two. Delta V is equal to E. Okay, that means 2 pi r times E is equal to negative pi r squared dB over dt. Dividing both sides by 2 pi r, so E is equal to negative r over 2 dB over dt. How about that? Good? Okay. When you do this, you almost think in terms of magnitude and just do not care too much about this negative sign because direction of the field and direction of the B is like they don't line up. Okay? So, general form. Remember Faraday's induction? Right? This thingy, EMF was negative this thingy. But instead of that, we are going to substitute that with this integral here. Remember, we equated the two. So this is a general form of Faraday's law of induction. And we use this a lot like we use Gauss's law. But difference is this is not Gaussian like double integral. This is a single line integral in a loop. Okay, it's more like Amperian loop. Do you remember Amperian loop? Was a B here and then still line integral around. B ds and the other side was. Let's write it down. It was like this, right? Inside. Right, that thing. So it's like it's similar looking thingy. Except this side is the derivative of the total flux count now. Good. Now this, you heard about like Maxwell's equation? One of the Maxwell's equations, these are famous four equations in ENM. First one happens to be Gauss's law, by the way. And this is like number 3, I think. And they are famous equations. Okay. We are almost there, so hang in there. Okay. We have a solenoid. Okay. That will create, let's say current goes around in this direction up and then goes around the solenoid. Okay? Can you imagine then that will create this thingy inside the rod to be magnetized? Can you tell me which side is north and which side is south? Right hand rule. Wrap your fingers around, right hand fingers around the solenoid. Remember it goes out and then goes back.
I'm trying to figure out how to do that with my right hand.
Like that.
So then,
So this side is north, right? And this side is south. So it creates the magnetic field inside moving that direction inside the solenoid. You know what I'm saying? And of course it goes around outside like that too, just like regular magnet does. And if it's long enough, then we can ignore there's nothing outside, right? If it's tightly wound, these wires are tight enough and this solenoid is long enough, then there's nothing, it's just internal. There's one that's flowing inside like this. Okay. Now, then we have to, then we vary this because that really does not induce any current outside or electric field outside. But now we vary this electric current, and this is a typical alternating current, cosine function. Then what happens to the electric field outside? Right? Because the change of the magnetic field, because if we change the current, it'll change the strength of the magnetic field inside. Once again, if I put a cosine function, then this direction will switch back and forth. Then north and south will switch back and forth. That's going to change the magnetic field a lot, right? Then you think amount of electric current or electric field induced around it will also be sinusoidal function, at least? Yeah. Okay. So let's figure that out. Okay. So part A outside, but radius R, and part B inside, if R is smaller than this capital R. So we have to figure it out both ways. Okay. The whole idea is to get you familiarized with this. Okay. So electric field E dot ds is equal to opposite of that thing E. You know what I'm saying? Okay. And the left-hand side, E constant outside, and then you have ds like that. And on the right-hand side, we have, ooh, we don't know what, well, this is derivative of magnetic field and pi r square, isn't it? BA. We don't know what B is. Pi r square is constant. We don't know about what B is, right? This thing at least, E becomes, this is 2 pi r. So we'll say pi negative pi r squared dv dt. Okay? Usually B is given, but in this case it's not, right? This B is created by the current in the solenoid. So we have to compute that. You guys will hate me when I do this, but I'm going to shove this to the side. Or you can do yours right-hand side, but I'll just shove it to the side and calculate myself magnetic field created by this current. Okay? So remember, let's actually review this. B dot ds is equal to mu I inside, right? Space I. Now, I'm going to put my Amperian loop like this. Through inside. Okay? U. So this B dot, this line integral is not same as line integral here, right? This line integral on this side is that loop around in order to figure out the electric field around it. And this loop is the review of the other unit, right? Amperian loop. And then all of the wire counts inside. You get it? So it's not just I, but it has to be Ni, right? Well, it's not really. Whatever they call it N, I think it's the density. Where's N? N turns per unit length, right? So if we call this thing L from here to here, and this has to be NLI. Do you agree? Okay, well then. Remember, if this solenoid is long enough and tightly wound enough, there's no magnetic field outside. So only thing that counts in this line integrals inside. So this side becomes B at the center, constant, and L. Good. And on the right-hand side is the mu n L I. And divide both sides by L. So your B, we have our function B, is equal to mu n I. You get it? And now, remember I is given right here is our alternating current. So substitute that in, so mu n I max amplitude, and then cosine omega t. Then, huh? Now we can come back here and that substitute it here and integrate. Get it? So, oh, let's finish this thingy up. So as I don't want to write it on both sides. So your E, dividing both sides by 2 pi r. Ooh, I messed up. Do you know where I messed up? This r squared. Pi r squared, except that r is this capital R, isn't it? Because it doesn't really depend on the size of our loop. Only magnetic field is inside the solenoid. That was close. So this is capital R squared. Yes.
Are we trying to find the inside or the outside?
Well, we have to do both. So part A, it is capital R. Part B is inside, so it's lowercase r. So we'll actually do both. Like I never mistakenly did part B. But we'll do part A first. Because from here, you can just think about it and figure out part B really fast. Okay? Okay, dividing both sides by 2 pi r. So we have negative pi cancels r squared over 2 lowercase r. And then dv dt. Good? Now remember, b is given right here. It's a cosine function. So derivative of cosine makes it negative sign, so cancel that negative sign. So we'll have r squared over 2r, and then we have this constant mu n I max, and then chain rule omega, and then sine omega t is the electric field induced outside of the solenoid, distance r away from the center of the solenoid. Thing, huh? And as we expected, this is sinusoidal function as well. Okay, part B. Part B, if you think about it, is really easy now because like think about what we did. Only change is this is lowercase r on the other side, right? So dividing by it, just substitute lowercase r here instead of uppercase r squared right there. So that'll cancel. So what would be part mu n I max, I'll just dump everything over 2, and then r, and then sine omega t. How about that? And predictably, this is like similar. It's a linear function. If you're at the center, there's nothing, and if you go outside, it goes out, directly varying with r. And once you come outside of solenoid, it's inverse variation. Okay, quick thing about generators, and then we'll call it a day. Okay, this is how you generate electricity. Like there's a hydro plant, water rotates the turbine or whatever thing it rotates, right? So you have to have some kind of external force, torque, rotating this thing. Steam, water, whatever. And then inside, there's this kind of mechanism, except if that loop has like many turns instead of just one. They just only drew one here, but that's like more like multiple solenoid loop like that, okay? And you have permanent magnet, north and the south. And they make inside little curvy to make that magnetic field a little more uniform. Okay? Now, let's think about this. As this thing moves in a magnetic field, you see it will feel the change of the magnetic field, right? From north to south. That will induce the current, whichever the direction it will be, right? It's kind of tricky we have to do that whole thing to figure it out which direction it is. And then this thing moves from south to north. So if you will, that P field is decreasing on that upper line wire because it's from north to south, and this is increasing, right? And then they switch back and forth. So conceptually, it has to be some kind of sinusoidal function, your induced EMF. Okay? Now, let's see if that reasoning is correct. Okay? So first of all, it rotates. And remember there's a dot product, right? This thingy. Let's just say VA now, right? Area of that loop. This is a side view. And then cosine theta now, because the field is not exactly perpendicular to the normal, right? Okay. Now, here, B stays constant. This is permanent magnet. Area stays constant, but it changes the angle around it. That makes sense. That changes the amount of field lines inside the loop. If I draw the picture, let me draw it right here. Right? Only amount of field going through is the A times cosine theta, isn't it? And that angle being theta. No, the other angle is theta. That makes sense to you? Wait, no, I was right the first time. This angle is theta. Good. So when this angle becomes 90 degrees, then nothing goes through the loop. And this thing angle becomes zero, it stands up, so that everything has to do with that area. Okay, so this has to be the total amount of flux count, right? Instead of BA, now it has a cosine theta term. Good. Well then, what's theta? Theta is a function, right? Remember, angular velocity is equal to d theta over dt. So that tells you theta is equal to angular velocity times t. If it's constant angular velocity, which it is in most cases. So substitute that here. So this flux is BA cosine omega t. Good. Now it's easy. Then induced EMF, the voltage coming out of this is this, of course. However, I deliberately left a little space. Do you know why? Number of turns of this loop. If there are two loops, right? And then it'll double. If there are three, then it'll triple. So n turns times this. Okay. When we differentiate this thingy, we have the function. So n, b, a, that negative cosine derivative will become negative sign, cancel. And then omega, and then sine omega t. So this is how you generate alternating current. And this is such a natural thing to do, so that's why we use alternating current in household electricity. Nikola Tesla came up with this.